Hi, Assalamualaikum sir. My name is Nur AFIFAH binti Muhammad SENAWI from group 11. So, I want to show you for part A. Okay, basically this is my first circuit for part A. I've set the DC current for 10 milliampere and the resistor for 100 ohm. And then I put the voltage probe and I run the circuit. Okay, after I run the circuit, I can see that the voltage for this circuit is 1 volt. Okay, to find the resistor by calculation, I use the formula R equal to voltage over current. So the voltage is 1 and the current is 10 milliampere. I change it to 10 multiply 10 power of negative 3 ampere, and then I got the resistor value is 100 ohms. After calculate manually, I found that multi-sim resistor value is 100 ohms, same to my calculation value that resistor value is 100 ohms. Okay, this is my second circuit for part A. I've set the voltage for this circuit for 10 volt and resistor for 100 ohms, and then I put the voltage probe to make sure the voltage in this circuit is 10 volt. So I also put the ammeter probes to check the current. After I run the circuit, I found that the value for ammeter is 100 milliampere. Okay, for table number 2, I need to measure the current in this circuit based on the voltage. So, I will change the voltage to 8 volt and I will run again the circuit and I'll find the current now is 80 milliampere. And then I will repeat this step to change the voltage for 6 volt, 4 volt, 2 volt and 0 volt. After changing all the voltage in multisim, I've got the value for current in the circuit in multisim. This is the sample for calculation table 2. So I use the formula current equal to voltage over resistor, and then so the voltage is 10 and the resistor value is 100 ohms. So I got the current for 0.1 ampere, and then I change it to milliampere. So current now is 100 milliampere. Okay, now I'm showing you the calculated value for current in the second circuit. So this is my table for table 2. Okay, this is my final graph for voltage against current. Based on the equation for the graph V equal to IR, I found the gradient is actually equal to R. So I got the R equal to Y2 minus Y1 over X2 minus X1. So I take the value from the graph is 10 minus 0. And then 100 minus 0 times 10 power of negative 3 ampere. So I got the gradient or the R value for this table is 100 ohms.
Good morning, sir. I'm Kaya from Group 11. So this is my Figure 3 resistive circuit for lab sheet 7. So I'll try and run it. Okay, as you can see, the reason why I put a current probe in front of the junction is to find the total current source from the battery, which is 50.283 milliamps. So we can see that as it enter, there's a parallel circuit. So then there will be a difference in the amount of current flowing in different pathways. But then if you add them together here, it will become 50.283, which is equal to the before it enters the junction. So we can verify Kirchhoff's current law from that situation. And we'll look into the voltage probe. The reason why I put a reference voltage here is to specify which voltage drop I'm trying to measure. If I don't put the voltage probe, it will then measure the ground instead. and this will cause it to measure the whole circuit later, which does not give you an accurate result. So that's why we wear a reference probe. And to verify Kirchhoff's current law, like I said just now, I added 27.027 and 23.256, and I get 50.283. For example, my calculation, something like that. Get a node, junction, and so on. Okay, so, and then we'll talk about the Kirchhoff's voltage law. Kirchhoff's voltage law states that sum of voltage in an enclosed loop is 0. So the calculation, I got like 0. This is to first I follow the rule, which is sum of all is 0. But why is that so? We'll look in a bit in the lab sheet for a while. I want to justify why is it 0, because when we look at the third one, VCE has no resistor, so we can assume that there's no voltage drop across the wire here, so that's why it becomes 0. And the second one, VEF, it's in a negative direction, so that's why the voltage will be assumed as negative 10 volts. Finally, FA here, there's no resistor, so that's why I put it as 0. But resistor all is in here, so that's why the voltage drop occurs in here only instead of like the wires here. Okay, so and from there we can verify Kirchhoff's current law and Kirchhoff's voltage law. So that's all from me. Thank you.